Welcome to 7.5. This is Algebra, Chapter 7, Section 5. Special types of linear systems. Today we have a quick lesson, a short lesson, looking at the number of solutions possible in a linear system. The linear systems that we're dealing with, lines. So these are my imaginary lines. Imagine they extend forever, right? And so what is the possible number of solutions? First of all, what is a solution of a linear system? Tom? A point where they intersect, right? So if I had the equations written down for these lines, they might intersect at a single point. Remember, that point will work in both equations. It will make both equations true, right? Okay, so we know what a solution is. You're all good at that. But now today we're looking at all the possible number of solutions. We looked at this way back when, at the beginning of the chapter, just as a preview. But do you remember the other possibilities? So we might have a system like this. Two lines where there is how many solutions here? One solution, right? What are the other possibilities with a two-line system?
None and infinite.
Okay, what would a none system look like? Matthew?
Parallel.
Parallel. Okay, so if we have a linear system like this, even if they're horizontal or vertical, whatever, they're never going to intersect if their slopes are
Equal.
the same, right? So no solution is a possibility, right? And then the last possibility is
Infinite.
infinite. And what does that look like with the linear system?
The lines are on the
Do you remember what the name of that is? It's a C word. Coinciding. Can you say that? Coinciding lines. Okay, so coinciding lines is the same line. When you get the equations, they don't look the same, but when you transform them, they're the same line. Or if you use elimination, you add them, you find out everything disappears or something, you know, you get a true statement, you find out they really were the same equation. And so you have infinite solutions. Okay? So here are what we just stated. One solution is found in intersecting lines. Those are lines which have different slopes. Somewhere they're going to intersect. Okay? That is known as a consistent, independent system. We just said zero are our parallel lines. We know that they have the same slope. That is known as an inconsistent system. And finally, infinite solutions are coinciding lines. They have the same slope and the same y-intercept. It's called a consistent dependent system. So pause the video, take it down if you need to. I mean, the fact is, you really are more often going to be dealing with these systems as equations. And so on a test, you're not going to be asked to necessarily graph a lot. You're going to be asked to solve the system. So here we have, oh, you can't see it. Let me unfreeze it. Here we have, I'm going to give you three systems now. And without graphing, can you identify the number of solutions? So you're trying to determine, are these lines intersecting, are these lines parallel, or are they the same line really, right? But when you're given these equations in your assignment or on a test, you're probably going to fall back on the processes that we already learned, right? So rather than graph this, we've learned what were the other methods in solving a system? Elimination or substitution. That's what we're going to do. And in this case, when you look at these, what do you want to do? Elimination. If we add these two equations together, we can see that the y is canceling, right? The y goes away. So what are we and actually the x goes away too. Look at that. The x goes away. So what's left on the left side?
Zero.
Zero. Don't forget that. Sometimes people just think there's nothing there and they just throw away an equation and bring down the other side. It's not uncommon for me to see that. I was talking to 7th grade about that today too. When both of these things go away, we've got to say there's zero there, right? 3x or 5x minus 5x is 0. So put 0 down. And 6 plus 3 is 9. So here, this is what we end up with. 0 equals 9. So now, 0 does not equal 9. This is not a true statement. So how many solutions does the system have?
Not zero.
So what kind of lines were these? These were parallel. And to prove that, you can go over here and put them into slope-intercept form if you want, right? if we put these into slope-intercept form, the first one we would subtract 5x from both sides and we would end up with 3y equals negative 5x plus 6. And when you divide every term by 3, we end up with a 2 here, right? So we end up with y equals negative 5/3 x plus 2. And over here, when we add 5x this time, we end up with negative 3y equals 5x, what, plus 3? And now when we divide by negative 3, do you see what we get? We get the same slope. We get negative 5/3 x, but what is our y-intercept here? Do you see it? It's negative 1. You don't have to go through this to answer the question, but when we look at it now, we can see that we have a common slope, right? Different y-intercept. We know what that looks like on a graph. It's lines that are parallel. So there is no solution. When you end up with a false statement like this, there's no solution. Okay? You would write no solution.
So shall we put y-intercept form?
If the question is, how many solutions, you would write no solution. If you were worried about this, whether you were correct or not, you could check it just the way we did. We put it into slope-intercept form, and we saw same slope, different y-intercept. It's a good check. The problem in a test situation with this is that a lot of times students will get carried away with no solution. No solution, no solution, no solution. And there were solutions or there were infinite, you know? So be careful. Make sure that you are absolutely correct when you say no solution. Will there be a question where there is no solution on the test?
Yes.
Yes. Will I put 5 of them in a row?
No.
The probability is not. Could I do that?
Yes.
Yeah.
I could, but I probably won't. Okay. Maybe I will this year though.
No.
Just kidding. Okay, so try this one. What is this? Here's another system of equations. How might a person choose to solve this system? If you weren't going to graph, you would probably do what? Say it. Substitution. Why substitution, Sabrina? Good. We already have an isolated variable, right? So substitution. Plugging that in, that expression in for y. So we come over here, we plug y into the second equation. Negative 6x plus 3 times 2x minus 4 equals negative 12. Okay, so who wants to quickly walk us through it? Say it so I can write it. What happens, Kate?
We get negative 6x plus 6x.
6x, weird, okay.
And then negative 12.
Equals negative 12. So what is negative 6x plus 6x?
0.
0. So we end up with negative 12 equals negative 12. Do we want to keep going? Does negative 12 equal negative 12?
No. Wait, yes.
No.
Oh, I thought you said does negative 12 equal 12?
But negative 12 does equal negative 12, doesn't
Yes,
it?
yes.
So what can we say? How many solutions? Infinite, because guess what? These lines are, Jack, these lines are the same line, aren't they? So look at that. If we were to change the second equation into slope-intercept form, imagine we could divide 3 out of everything. Do you see that? And we would end up with a negative 2 here, negative 2x plus y equals, dividing by 3, we get what? Negative 4? And now we add the 2x to both sides. Do we have the same equation? Do we have the same equation? Yes, we do. It's the same equation, which is why we have infinite solutions. Okay? So when you get a true statement, you know you now have infinite solutions. But when we had a false statement up above, we had no solution. Okay?
Interesting.
Probably going to be one solution for your notes. I don't know. Try it. How would a person go about solving this third system here? What do you think, Jenna? What would you do?
I would use elimination.
Okay, so how would you use elimination? I would use elimination too. And that's because we have a common coefficient, right? And so what would you do?
I would subtract.
Subtract the second equation? Or the first equation?
Well, I would subtract both of them together.
Okay, so she's going to subtract the second equation. And so when we subtract, we're really adding the opposite of each term, right? So I just like to say opposite, 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 right? And now add. She's subtracting by adding the opposite of each term, which leaves us with what here, Jenna?
X minus 2x would be
1x minus 2x.
so negative x.
Negative x. These are 0 equals negative 15,
3.
3. And so what does x equal?
X equals negative 3.
X equals negative 3. Okay, if x equals negative 3, can we find y? Let's go ahead and find it. In the original, negative 3 minus 3y equals negative 15. How would you solve this, Haley?
So you have 3, and you have negative 3y equals, or negative 12, and then you divide by negative 3, and then you get y equals.
There it is. One solution. Okay, so when you have one solution, you have one solution, and you're happy. You have one. What type of lines were these? These were the intersecting. Where's my other line? It's really a line segment, but okay, intersecting. They just had one solution. So you solved it, you got it, and you're happy, right? Are you happy?
Yes.
Here you go. Nice little assignment for you. Enjoy.
Is there
Have
gonna be a
fun.
second day?